Okay, welcome everybody. So today we have Chia-Yi Ju, and he will talk about Einstein's quantum elevator. And what that means is hermitization of non-Hermitian Hamiltonians via a general Vielbein formalism. So when you're ready, just go ahead.
Okay, yeah, thank you very much. Can you hear me now?
Yes, we can hear you well.
Okay, good. So today, what I'm going to talk about is that we're going to hermitize the non-Hermitian Hamiltonians with some geometrical tools. But before we start hermitizing anything, okay, let's talk about one of the biggest news these days in physics. That is, we have another photo of a black hole. So this is a rotating black hole called Sagittarius A star. And we know that this black hole comes from the general relativity. And that is also another victory of Einstein's. So now I want to talk about how we come from gravity to this general relativity, which is the bending of the space-time. So the story begins with the Newton and apple. So we know that when Newton was falling on an apple, I know it's different from the typical story, but we know that the story was made up anyway, so let's just make it fair. So anyway, the Newton was falling on an apple, and he realized that he was falling in the same acceleration as another falling apple, and they're all proportional to their own masses. And this is something that we already learned from general physics class. And another thing that we learned from general physics class is the fictitious force. So if we're in an accelerating frame, then we find that there is a force, a fictitious force, that is also proportional to the mass of the object. And now here is some coincidence between these two. They're all proportional to some acceleration, and they're proportional to the mass of the object. Excuse me. So maybe this is a coincidence, but maybe not. Anyhow, we're not bold enough to claim that they're the same. Because if they're the same, then that means there is an accelerating frame. And then what is the force that's holding us on the surface of this Earth? So we're not bold enough to claim that. But Einstein himself is a dreamer. He dreams big, but he also works hard. So he thought that these two, the similarity between these two are not a coincidence. He thought that these two are the same forces. But how do we resolve the problem that there is something called gravity that's holding us onto the surface of this Earth? So he thought that maybe the space-time is not as rigid as we originally thought. Maybe that can be bent in some way. So the idea to resolve this, to resolve the paradoxes, is that assuming that this blue thing is an object that's moving upward, and somehow there is a gravitational source, another mass, that is coming in from the left-hand side of the screen. And now the space-time is curved. It's bent by the source of gravity. So the mass bends the space-time. Now we see that this object is tending to move upward. But from the point of view of this object, it feels that it's actually turning a little bit to the right. So when it's turning to the right, that means it feels a force, a fictitious force, the centrifugal force that is pointing toward the source of the gravity. And that is actually a gravity. So gravity is nothing but a fictitious force in Einstein's theory. And this thing so far is classical. Einstein also worked on something that is quantum. So he's interested in quantum physics as well, although he didn't believe that quantum mechanics is complete. So he came up with an idea, together with two other people, so Einstein, Podolsky, and Rosen, these three people come up with a thought experiment. They thought that if there is a spin 0 particle that somehow breaks into two spin 1/2 particles. So in order to preserve the angular momentum, if one of them is spin up, then the other has to be spin down, and vice versa. So now we have so many choices. So the particle on the left-hand side can be spin up or spin down. And the particle on the right-hand side can also be spin up or spin down. Once you measure one of the particles, say let's measure the left-hand one, and you get spin up. In order to preserve this state, to preserve the angular momentum, this state should, according to these great people, EPR, should send an information to the other side to ask them to get the story straight. So you have to be spin down. And if you measure spin down, then in order to get the alibi straight, well, it has to send a message to the other side saying that you have to be spin up. But nowadays, we know that this is not the case. Now we understand it differently. When it's breaking into two pieces, they're not actually separated. They're spatially separated, but in fact, they're one piece. So instead of having spin up, down, the other side also have spin up, down. It's actually a whole package. It's spin up and the other has to be down, like this one. Or if it's spin down, the other side has to be spin up. They're in a whole package. You don't get one piece by one piece. So it's a whole package. And this has a very important consequence these days. That is, in quantum information, an entangled state is really important. So if these two are not entangled, they can have their own spins. But once they're entangled, for example, this state, if you measure, say, the left-hand one, and you get spin up, then the other side automatically collapse to spin down. And not just automatically, it's instantaneously collapsed to spin down. Now we're thinking, some people are thinking that maybe you can use this and set up some protocol so we can send a message to a faraway distance, because entanglement state itself doesn't know anything about distance. If you have one measurement, then it collapses the other side as well. So can we do that? It turns out that this is impossible. And here's a quick observation. So if we have two particles, for simplicity, let's call the left-hand one particle 1 and the other side particle 2. If we make the measurement of particle 1 first, then you might get spin up, and that will collapse the other side to spin down because of this state. So the other side is spin down, and that happens 50% of the time. You might also get spin down and collapse the other side to spin up 50% of the time. And that's when you measure particle 1 first. On the other hand, if we measure particle 2 first, you'll get 50% spin down and also 50% spin up. So if we only have the access to one of the parties, say if we only we only measure particle 2, we get 50% spin up, 50% spin down, no matter if particle 1 has been measured or not. And this is not specifically for this state. You can change to any arbitrary state. So for example, this state, you'll get the same result. If you're only measuring one of the parties, you don't see any differences. And that is telling us we cannot send a message through entanglement state alone. And the reason is because we don't have the control over the measured outcomes. And this has a name. It's called a no-signaling theorem. So here is a list of no-go theorems in quantum mechanics. So these can be argued that this has to be satisfied in quantum mechanics. But in order to show that whether quantum mechanics actually is compatible with this, we have to go back to the Schrodinger's equation. This is arguably one of the most important and most fundamental equation in quantum mechanics. But in our textbooks, we know that this equation, Schrodinger's equation, the Hamiltonian, has to be Hermitian. But why is the reason for this? I mean, this one seems a little bit artificial. If we found a system that can be described by a non-Hermitian Hamiltonian, then who are we to actually forbid it? So maybe let's relax this condition a little bit and claim that all the Schrödinger's equation with any Hamiltonian that describes a system well to be a physical equation. So we can relax this condition a little bit, but the first obstacle, the very big obstacle that came up is a study in 2014 that people found. A study showed that actually they found a non-Hermitian system that actually violates the no signaling principle, which is the no signaling theorem that we talked about. So what they found was, it seems that no signaling theorem is incompatible with non-Hermitian Hamiltonians. And that is not the only obstacle. It's the beginning of all the obstacles. That we've said that there are some arguments saying that these no-go theorems should hold in quantum mechanics, but these has only been proven under the condition that the Hamiltonian is Hermitian. When it comes to non-Hermitian Hamiltonians, it turns out that these are all violated in the non-Hermitian regime. And that raises the debate between the different people, different groups. Some people believe that non-Hermitian system just doesn't exist. Some people think that they might exist, but as an effective theory. And some people even believe that quantum mechanics is wrong. But anyhow, I want to pause here a little bit. Some people might start thinking, what is this guy talking about? He started with a gravitational theory, general relativity, a black hole, which has nothing to do with these things that he's talking about. And that's exactly the point I want to make. They are closely related. So in fact, all these paradoxes can be resolved if we consider this quantum mechanics in terms of geometrical theory. So now, if that's the case, then we can treat classical mechanics, which is general relativity, using differential geometry, and also quantum mechanics using the same idea here. So we have a multi-purpose tool. And this is very popular these days, multi-purpose tool. For example, well, if I want to, say, have dinner, then I want to pick up my food, my solid food, broccoli, fries, or chips, depending on where you're from, using forks. And if I want to pick up some liquid-like food, like broth or soup, or even ice creams, we use spoons. But what if we can merge these two together? And we know that this is doable because there's something called spork, and that can do both things. But I'm from Taiwan. As an Asian, I don't use fork that much. So I was thinking, hey, if there's an idea of this spork, can we find something that merges chopsticks with spoons? And after some search, I actually found something, but I thought this would have some like very fancy name, like spoonticks or chapoons, I don't know, just something fancy, but turns out it's called a pair of tones. So anyway, kidding aside, it's good to have one tool that can be used both on classical mechanics and also on quantum mechanics. I think somebody raised a hand.
Yes. Yeah, it's just a quick question.
Yes.
A PT symmetric Hamiltonian may not be Hermitian, but if it's got a complete basis and all the eigenvalues are real, it can be brought to a Hermitian form by a similarity transform. So the question is, those theorems on no signaling, are they claiming that that no signaling is violated by a similarity transform? Or are they only considering PT theories for which the similarity transform is ill-defined?
As far as I understand, they didn't do a similar transformation. So they only look at the PD-symmetric quantum mechanics, the PD-symmetric system. And I'll elaborate more later, actually. So
I mean, it seems to me trivial that I know whatever this no signaling hypothesis is, or requirement is, it can't possibly be modified by a similarity transformation. So I just don't understand the content of the claim.
So the idea is they are using the wrong inner product. As we know that in PD-symmetric quantum system, you don't use the conventional broad and cat, you have to modify the broad and cat. But as far as I understand, they use the conventional ones. And I think that's the reason why they get this really weird result.
That's not PT theory.
No.
So then the whole thing's without content.
No.
Okay, thank you.
Thank you.
I think what Philip was just saying is you neglected to say that the paper was wrong.
Yeah. well, I don't know. I didn't say that. They forgot to put that in anyway.
That's a very, very, very serious omission.
Wow.
Yeah, I agree with that.
I mean, I don't know of any PT symmetry paper which has ever suggested that you use the Dirac norm. So, I mean, it's well known that you don't.
Well, yeah, anyway, that is a part that I'm going to talk about later.
Okay, so, anyway, fine.
Okay, if you don't
back to the chopsticks.
Yeah, chopsticks. Okay, so where am I? Yeah, chopsticks. And now I forgot where I'm going to do. Okay, yeah, so something that convinced me that we neglected something, as Professor Bender said, is that we forgot to take that geometric idea into consideration. And what convinces me is this equation, the Schrödinger's equation. We're so familiar with that, but I don't know about you. For me, when I was a student, I look at this equation. I think that this is nothing but a differential equation. You put something physical in, and then you get something physical out, and that's pretty much it. But these days, we look closer into this equation, and we found that there is some geometric information encoded in this equation. And I'm going to show what exactly is that geometric idea there. So let's come up with let's start with something called parallel transport. So what is a parallel transport? For example, if we have a vector here, the blue vector, and I want to transport this along this orange line parallelly, then this is exactly what you think. So we're parallel transporting this vector. And if we're parallel transporting this vector along this orange line to the other end, then yeah, the same thing, it's just parallelly transported. And when we finally propagate this vector back, we get the original vector. But if we're on a different geometrical space, for example, this sphere, if we're limited on this sphere here, and we still want to make a parallel transport along this big triangle, then when we move from the North Pole to the equator, we'll find that this vector is a little bit strange, but let's go on, parallel transport it, and finally we transport it back, you will find that the vector doesn't go back to the self. And from our point of view, well, this is a little bit strange because when we're at the North Pole, the vector was pointing horizontally, but when we reached the equator, it seems that it's pointing a little bit downward. So is this really a parallel transport? So let's look at the same thing in first person point of view. So if we're now sitting at the North Pole, then we're pointing somewhere and we're moving along where we're pointing at. So when we reached the equator, well, we don't think that anything happened, but you're pointing southward. And if we're propagating along this orange line and propagate back, you'll find that, yeah, indeed, we're pointing in a different direction. But how do we actually describe this mathematically? So now we have this blue vector v. So this v is a vector vx, ex plus vy, uy. And now we're using Einstein's convention. So we can also use this vector, rewrite this vx, ex, and vy plus ey, vy, sorry, vy, uy as this thing. So the repeating indices means that we have to sum over all the possibility. And in this case, it's x and y. Okay, if we're parallel transporting this v along this direction, the x direction, that means the vector is not changing in this direction. So the equation for this is that the partial derivative on this vector v is equal to 0. And in terms of the components, the small v's, it's just the partial derivative on these small v's are also equal to 0. But this equation is different when you're on a different geometry. So we still have a vector v, which is v theta e theta plus e phi, sorry, v phi e phi. A little bit tongue twisting. So in order to parallel transport this vector v along this direction, the phi direction, we want this capital V, the vector itself, to be constant along this phi direction. So partial phi on v equals 0. But in terms of these components, the small v's, it's this notation nabla phi on this v mu. This is defined to be, okay, the first term, partial phi on v mu. This is understandable. This is just the partial so the differentiation of this v along this phi direction to be, I'm sorry, this is just the partial derivative on phi direction. But the second term here, the gamma thing, that comes from the partial differentiation on this vector, the unit vector, because this vector is changing on the sphere. So it's not 0 anymore, and it has some contribution. So this one, if we're talking about the parallel transport on the components, this thing is the parallel transport equation for the components. And this is called covariant derivative or connections. But now the question is, how does this relate to something we just talked about, the Schrodinger's equation? So let's rewrite this partial differential, the covariant derivative in general. So this is something that you can find in textbooks. A parallel transport is just the covariant derivative of a vector is equal to 0. So that means it's this thing equals to 0. But let's rewrite this form a little bit. Let's combine all the small v's into one column vector, and let's call it capital V here. So this is a state, this is a vector that has all the components here. And we also combine all the gamma with mu, nu, rho into one square matrix here. Then this equation here can be rewritten in terms of matrices. So it's 0 equals this covariant derivative, that is the partial differentiation on V vector, and also an operator gamma acting on this V. And I hope that this looks a little bit familiar already. But let's move forward and let's look at this parallel transport again. But now let's choose very specific mu and very specific gamma. So let's take this mu to be t in time direction. And this v, let's just rename it as psi. And this gamma t to be IH. We don't know what h is right now. But then the parallel transport equation becomes this equation here. And by just rewriting these equations, like we move some terms to the left, some terms to the right, and we'll find that this is exactly the Schrodinger's equation. So now we have a guess, like this parallel transport, the Schrodinger's equation actually looks like the parallel transport equation. So this might very well be a geometrical equation. because if it looks like a dog, it quacks like a dog, it swims like a dog, then why don't we treat it as a duck, right? And we can use this idea to further, I think we have another question.
Yeah, I'm not disagreeing with you. The Schrödinger equation basically says that the Hamiltonian is the generator of time translations, and general coordinate invariance is just local translations.
Yeah, but by local, I can also make this Hamiltonian time dependent. So
No, fine. You certainly can. And the whole idea of general relativity is that general coordinate invariance is just the generalization of what would otherwise have been global translation invariance. And that's where we get the Schrödinger equation initially from global time invariance. And you're just making it local, which is fine. And you have to introduce the connection to do so. The only change is that in the gravitational case, the Riemann tensor is non-zero.
Yes.
And so you can have curvilinear coordinates with a non-trivial connection, but that doesn't make the Riemann tensor non-zero. So the question is, do you have a geometric analog with the fact that in curvilinear coordinates you need to use a connection, or do you have an analog with gravity where you need to use a connection and have a non-vanishing Riemann tensor?
So far, no. The thing is,
so far you haven't put in a non-vanishing Riemann tensor. Okay.
The thing is, we only have one dimension. So far, we only have one dimension. And if you only have one dimension, then all the curvatures have to be zero. That's by construction. So we don't have any curvatures. So yeah, you can define the curvature, but that is trivially zero. I don't know if that answers your question.
Okay. So
but may I add to Phil's question? Do you claim that you have time reparameterization invariance in?
No.
Okay, but that's the essence of general relativity.
Well, at this point, we're just dealing with differential geometry, so not that much related to general relativity.
But also in differential geometry, all things geometrical are coordinate independent.
Yes. So that's what we are trying to do next, actually. So we're trying to change the coordinates, and that's how we hermitize the Hamiltonian.
Okay, so let's see.
Yeah, so I might answer your question later on.
Okay.
Okay, so anyway, we have a parallel transport equation, and that might help us determine the Hilbert space metric. So what exactly is a metric here? For a Euclidean plane, the inner product between U and V vector is just U1, V1 plus U2, V2, assuming two dimensions are only two dimensions involved. And that we can also rewrite this in terms of matrices. So we have U and V both are column vectors. So this U and V, the inner product between U and V, just U transpose acting on V. But for non-Euclidean planes, the inner product is more complicated, but still manageable. But since we're in a non-Euclidean planes, that means maybe some off-diagonal terms may get involved. And also the coefficient in front of every term doesn't have to be 1. And these coefficients are called the components of metric or fiber metric. And we can also rewrite this in terms of matrices. So it's just U transpose acting on this G vector and acting on a column vector V. But this is not specifically for non-Euclidean spaces. If we take this G to be identity, then this becomes the Euclidean, the inner product as well. So this one is very general. And let's look at the similarity here. So here it's U transpose acting on V. That's the inner product. But if we change this transpose to a dagger, then this looks very similar to bra acting on a cat. So what about this one? Maybe if we change that into change the transpose into a dagger, then this might give us something. So now we sort of extending from Euclidean Hilbert space to non-Euclidean Hilbert space. So the original Hilbert space, the conventional inner product, is just broad acting on the ket. But now we try to extend this idea. So now the inner product is not just broad acting on the ket. Maybe we have to squeeze in a metric operator G in between broad and ket. But since this is a Hilbert space, there are some properties that it has to match. So, or axioms. One of the first property is that when you switch the role of broad and ket, you get a complex conjugate. And the other one is the inner product of a vector with itself has to be greater or equal to 0. So we can translate these properties into some constraints on this G, the G operator. The first one translates to G has to be Hermitian. And the second one is that G has to be positive definite. That means that all the eigenvalues has to be greater than 0. But there are a whole bunch of operators that satisfies these conditions. We know that we have to find some other physical conditions to further refine the possible G's. And this is where the parallel transport, the Schrödinger equation, is coming in. So let's look at the parallel transport again. If we have a vector, the green one, and it's moving forward, then if it's moving forward, then it's not changing its direction. It's not even changing its size. If it's moving sideways, it's also stationary. It's still there, not stationary. It's also a constant there. Even if it's moving in a very weird trajectory, as long as it's a parallel transport, then it should not change its direction. And now we can add another vector here. If it's also parallel transported, then if we're moving forward, both of them are constants. And if we're moving sideways, they're constant. Even in a very weird trajectory, as long as they're parallelly transported, then the relative property between these two vectors remains the same. So that means, well, the inner product between these two things, if they're both being parallelly transported, then nothing should be changing. And now let's come back to the physical equation, the Schrödinger's equation. Okay, this is by definition, by construction, our construction, that this is a connection or covariant derivative, which is defined to be partial t plus IH acting on this the vector. And using the Schrödinger's equation, that this thing has to be 0. This is a physical property. And that is telling us that the Schrödinger's equation can be treated as a parallel transport. And if the metric has to be compatible with this parallel transport or the Schrödinger's equation, then that means the time, when it's moving in time direction, the inner product has to be a constant. So the time derivative on the inner product between two states has to be 0. So by a trivial calculation, we find that the covariant derivative on G is partial t on G minus IGH plus IH dagger G. And if they're compatible, this has to be 0. So we found a field equation here. Okay, so the field equation for the metric G is partial t on G minus IGH plus IH dagger G is 0. But now we made an assumption that the Schrödinger's equation is a parallel transport. This is mathematical. We made this assumption. In order to make sure that at least to check if we're on the right direction, we have to find some physical evidence. And the reason why we want to do this is because we found that these no-go theorems, they're incompatible. They were violated in the non-Hermitian regime. But if you take that field equation, the metric, put that back into the inner product, we can show that they hold in non-Hermitian regime as well. So this is a strong evidence for us that we're on the right direction. And another thing that we should check is if it is compatible, if it's consistent with what we already know. So let's look at the field equation. We found that one of the first observation we found is that the metric is trivial only if the system is Hermitian. That means the Hamiltonian is Hermitian. So if G is identity, then this Hamiltonian has to be Hermitian. And that is also the reason, at least for me, why all those strange or weird properties that people claim to have in the non-Hermitian system is because they try to use the conventional inner product, which is when G is identity. But this can only happen when the Hamiltonian is Hermitian. And well, the second thing that we found is that if you want to have a constant G, then this system has to be either Hermitian or pseudo-Hermitian. So if you plug this G, a constant G, back into the equation, you'll find that this H has to satisfy GH equals H dagger G. And this is the definition of pseudo-Hermitian. And by paraphrasing the first observation, that is, any non-Hermitian system implies non-trivial metric. That means if your Hamiltonian is non-Hermitian, then your metric is never going to be identity. And that's where a lot of problems are kicking in. Well, some people claim that there are greater than one probabilities. I'm sort of okay with that as long as you have a way to renormalize that. But the thing is, some people claim that there are negative probabilities, and I have no idea what that means. And I think the problem comes from this, the reason they use the conventional inner product, which should not be applicable when your system is non-Hermitian.
But sorry to interrupt you.
Yes.
Isn't this something we already know for about 20 years?
Yes, yeah. But we're just like trying to look at it from a geometrical point of view.
And you will tell us what that gains, right?
Yes, later on.
Okay.
So
May
yeah.
I also ask a question?
Yes, please.
What are the differences of your findings compared to the papers from 2018 by Ali Mostafazadeh and the group of Qinghai Wang? They considered actually also covariant derivatives, and the findings were quite similar, if not
exactly.
almost the same.
The result is the same, but we're actually using different approach.
Okay. It would be nice to hear what are the differences actually. At the moment, from the concept, it's almost one to one. So okay. So we will see it later.
Okay.
Most likely. Okay.
So the thing is, here is one of the problems. So non-Hermitian system implies a non-trivial metric, and sometimes this non-trivial metric could blur the physics, the underlying physics, and it's sort of hard to work with. So we're thinking, is there a way to avoid seeing these non-trivial metric? And it's been proposed by many of you that actually by changing your coordinate, you might see something different, but the same physics. So we use that idea, and so we borrow this idea from differential geometry. There's an idea called Vielbein. But let's talk about some general things, recall some general things first. So the inner product in a Euclidean space of a column vector V and V prime is V transpose acting on V prime. And the inner product between X and X prime in the Riemannian space is X transpose acting on GR. This GR is the metric. And then acting on on X prime. But because the Riemannian manifold metric is G has to be symmetric, it's a symmetric matrix, and its determinant is greater than 0. So that means we can decompose this GR into two pieces, ER transpose acting on ER, where this ER is a square matrix. Now we can change our frame, change the coordinate from X to a new coordinate theta, which this theta is just ER acting on X. And then the inner product, which was supposed to be X transpose acting on G on X prime, becomes just theta transpose acting on theta prime, which is exactly the same as the Euclidean space in the product. So now we seem to simplify this metric thing. So we don't see this complicated metric anymore. And we're using this idea and we applied it on, I'm sorry, I forgot to mention that this ER is called the Vielbein. And we're applying this onto our Hilbert space metric. Since our Hilbert space metric has to be Hermitian and it's positive definite, that means we can always decompose this into E dagger acting on E, where this E is a square matrix or an operator. And now we can change our frame from the original psi to this cat, psi cat, to the double squared cat, which is equal to this E acting on the cat psi. Then we find that this inner product, if we treat this the cat, the double squared cat bra to be just the Hermitian conjugate of the cat, and then the inner product actually becomes this bra acting on this E dagger E psi prime. This is very tongue twisting. And using this idea that this E dagger E is the metric, then we have this inner product, which looks like the conventional inner product, but it actually has this G implied. And that's what we call this E generalized Vielbein. So we use this idea, but this is not enough. We have to find the time evolution of the state. And if we find it, so the original state is governed by the Schrodinger's equation, but now the new one, the transformed state, the time evolution of that also looked like a Schrodinger's equation, but with a different Hamiltonian, which we call it H flat. And this is an induced Hamiltonian. And this induced Hamiltonian has, so this induced Hamiltonian is a combination of the original Hamiltonian and the Vielbein that you choose. And the most important thing is this H flat is always Hermitian. So by a simple calculation, you can find that this H flat is always equal to H flat dagger. So now we not only we sort of don't see the metric directly, and the evolution of it, this new state actually said it evolves like a Hermitian Hamiltonian. It evolves with a Hermitian Hamiltonian. And that's how we hermitize the evolution, time evolution of the states. So in a very non-rigorous sense, is that the original vector psi, it's moving in the complicated Hilbert space. But now we can use this Vielbein, generalized Vielbein, to sort of flatten this space and make it a hermitized Hilbert space. So the new states here, the original one, the Vielbein acting on the original one, that's the new state, then it's moving in a flat space. So the question is so for people, some people, they would think that this means that a non-Hermitian Hamiltonian is the same as using another Hermitian Hamiltonian. So non-Hermitian system is equivalent to a Hermitian system, but this is not true because the hermiticity is still there. The non-hermiticity is still there, but where does it go? It turns out the observables carries the non-hermiticity. I'm not saying the observables become non-Hermitian, but they carry the information of that. And the reason is because if we have a vector an operator O acting on the vector psi. This is still a vector. So we can define a vector O psi, which is just equal to the operator O acting on this vector psi. And we can transform this both these vectors using this Vielbein. And we want the new vector, new operator in the transformed space, the Hermitized space, O flat, acting on the transformed state is equal to the original one transformed into the Hermitized state. And by a quick calculation, we'll find that this O flat is equal to E, the Vielbein acting on this original operator, and then they act on the inverse of the Vielbein. So that's what we mean by observables carries the non-hermiticity, because the non-hermiticity is encoded in this Vielbein. So the new one, the transformed, the O flat carries this non-hermiticity. And we can make some observations here. So the eigenvalues of O and this O flat are the same because they're just a similar transformation. So if the original one is all real, the eigenvalues are all real, then the new one has to be all real as well. And
Philip has a question. Philip.
Yes.
I just have another quick question. But I could have started with a Hermitian Hamiltonian and transformed the way you've done with the Vielbein. But then, then you would have said that the transformed one retains the Hermitian information.
Yes, that's true. That's true.
So, I mean, and it seems to me the statement that you retain the non-hermiticity is not really, seems to be without physical content. This is only a comment.
Yes, but I wouldn't say so, because later on we're going to talk about the gauge transformation within this formalism, and we can always gauge transform that into a Hamiltonian, which is zero. It's non-dynamical, but we wouldn't say that all the Hamiltonians, all the systems are equivalent to a non-dynamical system. So I guess I'll talk about this later in the next slide.
I'm not sure about that. I mean, the G that you're using is positive definite.
Yes.
And you can never transform into a zero Hamiltonian.
Oh, and I'll show that later.
Okay.
Oh, maybe. Oh, I didn't put that in the slide, but we can always do that. Actually, I can make a quick comment. So this Vielbein, I mean, this E, if you think of this in terms of Heisenberg picture, the transformation of Heisenberg picture, that seems that the Schrödinger's equation is just partial T on states is equal to zero. But that doesn't mean that the system is non-dynamical. It's just the dynamics is encoded in this E.
Okay. I just want to repeat my question. Isn't this just the same what we have been doing for years? Isn't the epsilon just the Dyson map? And then the G is just E dagger E is just the same, no?
Well, I'm not sure that which part you're talking about. I mean,
it is the same.
Okay, I think what Chia-Yi is saying is that what we're used to in terms of transforming pseudo-Hermitian into Hermitian can be thought of as using a geometric connection.
Yes. So
now, it doesn't give you anything new, but he's giving you a prescription which is not the one that we've been using for the last 20 years.
We understand that, but the equations I'm seeing here and the equations we saw before, these are just the well-known equations. This is just exactly the same.
Yeah, that's correct.
And
that's his demonstration that his geometric approach gets you back to the standard pseudo-Hermitian approach.
Yes.
Yes. So the main point.
But he didn't say that yet. That it's the same. Sorry.
Oh,
no, so,
okay,
it looked like something new and surprising. And
I'm sorry
I don't
for the
think it is.
confusion. So the point is, well, actually we have some gauge transformation later on, but the thing is we're using a geometric approach to the things that we understand, and we can actually make the physics clearer using this geometric approach, because these geometric tools are well developed already.
Will you show this to us, that it becomes clearer?
Well,
let's wait. Let's continue.
Okay.
I don't see it yet.
Okay. So the thing is, so now we have a question. Is this the composition of metric G unique? And turns out the answer is no, because it's unique only up to a unitary transformation. It's a unitary gauge transformation. That is that we have this G, and we can compose this into E dagger E. And if we can add in an identity in between the E dagger and E, which is U dagger U, then we can rewrite this E as E prime. And this, so we get a new Vielbein, but it doesn't change the G, the metric. And so now we found that this formalism actually has a UN gauge symmetry, and this N is the dimension of the Hilbert space. And this does, the thing is why we call this a gauge symmetry is because that this does not affect the physics. That's the first thing. And the second thing is we're wondering, okay, now we know that this is definitely one of the similar it's one of the symmetry transformation. But is this the biggest group that can transform that of the gauge transformation? So we calculated all the degrees of freedom in this formalism, and we found that this is the largest group of the gauge transformation. So this unitary transformation is the largest group of this gauge symmetry. So yeah, I guess if we want to talk about something new, then this is how much time do I have? I guess I only have 5 minutes left.
Oh, go ahead. Go ahead.
Okay. So let me talk about something. Of course, this is not related to the Vielbein formalism anymore, but I want to show that this geometric approach is very useful, not only just for non-Hermitian quantum mechanics, but also for Hermitian quantum mechanics. So let me show you a table here. This is a table that's making a very uncomfort table. So I call it uncomfort table. So the thing is, on the left-hand side of this table here, we have this Hamiltonian, and it can depend on time t. And the state itself can also depend on time t as well. This thing here, we can use this Hamiltonian to find the time evolution of the state, which is the Schrodinger's equation. So this is the thing on the left-hand side. And on the right-hand side here, we have this Hamiltonian that can depend on both t and another parameter, physical parameter. This parameter can be any parameter that you can tune. For example, if you're putting a qubit in a magnetic field, then the magnetic field strength is something that we can tune. Then this is a parameter, or even the coupling between two particles or two sites. Those are the parameters that we can tune. Okay, so now the state depends on both time, and also if you tune the parameter, then this state evolution would definitely change. So that also depends on the Qs. But the evolution is only in time dimension. We can use the Schrodinger's equation to find its time evolution. But this table is driving me crazy. And I'll show you why. Let's rename all the t's, replace all the t's with x, and all the q's with y. On the left-hand side, it's okay. You have this Hamiltonian, which depends on x, and you have the vector depends on x. You have the x evolution. But on the right-hand side, you have Hamiltonian. You have something Hamiltonian that depends on both x and y. And this state depends on both x and y. And also, we have the Schrodinger's equation that tells us the evolution in x dimension. But what about the Y evolution. So the thing is, are we just being paranoid? Or are those parameters being discriminated? And in order to answer that, we have to use the geometry tool. So we literally look into the geometry of the system. So what we found is that all the parameters are sort of born equal, but some of them are very special, which is the time dimension. So we call it equality plus specialty equals hierarchy. It's like everybody is born equal, but somebody are richer, and some people are have more power. So there's hierarchy. And using the geometrical tool, we can find that the Schrödinger's equation determines the time evolution of the states. And we can use the geometrical idea. We can find the state evolution in the Q direction. So this equation here looks. This equation looks a lot like a Schrödinger's equation. But the thing is, this K can only be calculated using the Hamiltonian. So there's something special about the Hamiltonian, but we can still calculate this thing. Of course, I didn't show the full calculation because I knew the time is not going to be enough for us. But the thing is, this thing can only be found, it's only found because we know that we have this geometrical tool to deal with the this quantum mechanics. Then we find this equation, and we know that this looks a lot like what's called Bell connection, not Bell, Berry connection. But Berry connection only, so these states here, I have to mention that these states here are arbitrary states. Any arbitrary states. It's not focused, it's not limited to eigenstates or anything. If you want to get the Berry connection out of this K, you just have to make the projection onto eigenstates, then you get the Berry connection. So anyway, I want to sum up the talk today. So the first thing is we gave the Schrödinger's equation some geometrical meaning. And then we use that geometrical meaning to find the Hilbert space geometry, which is the metric. And then we use that to resolve some paradoxes in quantum mechanics, in non-Hermitian quantum mechanics to be more specific. And then we use that to hermitize the Hamiltonian using this Vielbein formalism. And that'll be all I want to talk about today. Thank you very much.
Thank you. Questions, comments?
Okay, I have quite a few. Okay, going right back to your very first picture of moving an arrow around. Oh, I'm sorry. I'm sorry. The first Vielbein picture where you moved an arrow around the Earth.
You mean the parallel transport, or?
Yes. Yeah, that's right. Now.
Okay.
Yes, fine. This is the same argument that finite rotations don't commute.
Yes.
I mean, that's it. And all you have done is, I mean, this is not criticism. What you're doing is you're taking that statement that in classical physics that finite rotations don't commute. You've introduced a connection, namely you've taken those same conditions in curvature.
But this is the wrong picture. It's on the sphere. You're referring to the sphere.
Yeah, on the sphere. Oh yes, but it was a moving picture, not a static one. Yes, that's the point. I mean, that's just the argument that finite rotations don't commute. Now, to go to quantum mechanics, we need infinitesimal rotations not to commute either. So
yes.
What I think you're doing is you're working instead of working in Cartesian coordinates, you're working in curvilinear coordinates, and you're writing Schrödinger theory in curvilinear coordinates. You get the general.
No, Philip. No. Here, the parallel transport doesn't come to itself because the sphere is curved. You get the holometry of the sphere.
No, I understand. On the specific example, this is a space with a non-zero Riemann tensor. But the proof, the usual, it's done in flat space. You take a book, you rotate it this way, then you rotate it that way, and you finish up with a difference, even in flat space, nothing to do with curved space, but he's doing flat space in curvilinear coordinates. He's not doing curved space in curvilinear coordinates, because even though that picture was introduced to emphasize the point, there's no, the fact that he's able to take his metric G and transform it to a diagonal metric means that the Riemann tensor is 0.
You're right.
That's what he's working with, which is okay. I mean, basically what he's noticed, I don't know, because somebody asked this a moment ago, maybe it's been noticed before, but that a non-Hermitian system is equivalent to a Hermitian system in non-Cartesian coordinates. That's basically what he's saying. And I think that statement, I think, is correct. And it gives a formalism, and of course it reproduces the formalism we're all familiar with, because it has to. It can't reproduce anything else.
You are talking about point canonical transformations in the quantum regime. So you take a Hamiltonian function of P and Q, and you change P and Q to something else.
Yes,
so
well, that's what we've been. That's what we do. That's how we get from non-Hermitian to Hermitian. But there may be something new here, which I don't think has been discussed in this talk. Suppose we do exactly what Chia-Yi has said, but in a geometry where the Riemann tensor is non-zero. I suspect that in that case, we could never get back to Hermitian.
But what is the Riemann tensor of a Hilbert space?
Well, whatever it was, somehow these connections that he's using, and this metric G, we construct from that G, we can construct a Riemann.
But the metric doesn't depend on the state. The metric doesn't depend on the state in Hilbert space, which would be the equivalent for Riemannian geometry.
The metric that he's working with, if you just took it as a metric in Riemannian geometry, would give you a zero.
Yes, but in Riemannian geometry, the metric depends on the coordinates of the space. Here,
no, the vanishing of the Riemann tensor does not.
May we need a little bit here? So,
Yes.
so the thing is, we don't have Riemannian geometry here, because what I didn't say here is that we're not actually on the tangent space. We're actually on the fiber bundle. And in fiber bundle, which is not a tangent space, we don't actually, I'm sorry?
No, you're absolutely right. What you're considering is actually a Hilbert space bundle.
Exactly, yes.
Not just a Hilbert space.
Right. So the best we can get is not a Riemann tensor. What the best we can get is a field strength. But I agree with you that if we can find a non-trivial, a non-zero field strength, then maybe we get something new. But so far, we haven't gotten that far yet.
Yeah, but you have a lot of no-go theorems concerning these Hilbert space bundles still from Steven Weinberg, from his books and so on. Dorsche Brody was discussing these points very often already in the early 2000s and so on. So this is one always returns to these problems just from another point of view.
Yeah, I think it seems to me that the thing that he could relax is that G be positive definite, because I think that's the thing that gives you a Hermitian theory where all the eigenvalues are real.
Well, no, it's quasi-hermiticity actually.
Yes, that's right. But you could relax that condition. I mean, because we know of PT symmetric systems where the eigenvalues are in a complex conjugate pair.
Yeah, but in this case, you will get all these more interesting geometric objects and much more interesting physical ingredients. You have all the phase transitions, all this in the geometric picture. So you have
I mean, it might, I don't know what's going on here, but it might be that the case where the eigenvalues are not real and the theory is PT symmetric might translate into something like a torsion. I mean, we have to work it out, but I think there's something going on here where you have to ask, well, suppose you have a system where the eigenvalues are in a complex conjugate pair. What changes? Something has to change because you can't come back to Hermitian. You can diagonalize, but you can't come back to Hermitian.
A simple criteria is just a topology, the underlying topology. In
Yes.
one case, you have something which is compact. In the other case, you have something which is non-compact. And you're just taking a Cartan inner product and this form, and you are seeing it just from Lie algebra theory that they are incompatible. Or you should use a kind of Fick rotation or something like this. So.
Well, I do think that his formalism could be extended to the case, to the PT case, where energy eigenvalues are in complex conjugate pairs.
Of course, yes.
And I think you may find some new geometric, I mean, there has to be, if his geometric approach is correct, then there has to be some geometric feature which would be different if the eigenvalues are not all real. And it's possible, I think I know the answer. Right at the beginning, you introduced you introduced the covariant derivative of V mu, and you included the ordinary derivative and the ordinary connection. But for Vielbeins, there's also a spin connection term. That equation, that should include an additional spin connection term. That's the correct definition of the covariant derivative of Vielbein is 0.
What this spinner what am I saying? That's also part of the reason why
it's got nothing to do with half integer spin.
I know what you mean, but the thing is that we have to introduce this Vielbein as well. So this is part of the reason why we want to work on.
I'm fine with the Vielbein, but the general statement is that the covariant derivative of the Vielbein is 0 only if you also include the spin connection.
Exactly, yes.
Yes, and maybe since you were able to get away without the spin connection, I was just thinking that maybe that's when the energies are real, that you didn't need the spin connection, and when the energies are in complex pairs, maybe you do. That was just a sort of guess, but that's a lot of calculation.
No, once you are just working with Vielbeins, you can just take just a standard theory 40 years ago concerning the Dirac equation in curved spacetime, and you have the same equations and just adding the additional coordinates, and here you have just time coordinate. That's all. And it's one-to-one, it's the matrix formalism and all the same.
No, but the Dirac equation in curved space, when you square it, doesn't give you the Klein-Gordon equation.
You have additional
you get an extra
torsion term, yes.
You get an extra term that depends on the Ricci scale.
Yeah, sure.
Yes. So that's, you see, when he tried to take the square root of the metric, the way he does it, that's the case where the Dirac equation would transform, it would give you the Klein-Gordon equation.
Yes.
If it doesn't give you the Klein-Gordon equation,
you have the additional torsion
because you're in a background geometry where the Riemann tensor is non-zero, then this formalism, I believe, could still work, but it must give you something new. That's just my guess.
Yeah, but it's sufficient just to take the Dirac equation in curved spacetime in the full formalism and just compare the structure elements that you are using, and you will immediately get all the remaining terms that are needed. So this is.
Can I ask a simple question? So your Vielbein epsilon is what people usually call the Dyson map, right?
Exactly.
Yes.
And can you see, because we know very well for many simple examples, what happens when you cross from the PT regime to the broken regime? What happens to your Vielbein in this case?
Well, actually, the thing is, when it's crossing, well, we don't know how they cross from one regime to another regime. In order to see how they crosses, actually, we have to go to something that we cannot go into details, which is the new thing that is not related to the Vielbein, actually. So we have this equation here. So the equation here. So we change the parameter. So for
No,
example,
this I will understand, but
Yes.
just in a simple example, have you worked out a 2x2 example or something
Yes.
simple where we can see what happens, you know?
yes, but,
Or we
but we're
get-
doing it.
You still have to convince us that this is useful.
Yeah, we're doing the piece by piece. So
Yeah.
we transformed the PT regime, the PT symmetric regime, the broken regime, and also the one that's on the exceptional point. So we calculate everything in detail.
Okay, but then when one does that in usual parameter space, and I guess you have to also work in this parameter space with
Yes.
your Vielbein, because that's where it lives, right?
Yes.
We see that something special happens, namely the metric breaks down, and this happens at the exceptional point. So does anything happen to your Vielbein? The same
No,
must happen,
Not just
but does the
Vielbein.
Vielbein formulation help us to understand this and what happens in this geometrical picture?
Actually,
Yeah.
in geometrical picture, yes, please.
You can just look at the equation, Vielbein equations for black hole and passing through the horizon.
No, leave out black hole, just the
No, not the
standard.
same thing. It's the same thing. It's the same thing as Karl Landsteiner explained in this ADS CFT talk. You
Yeah,
have
just let's stay just simple.
No,
Two
much
by two
simpler.
example, just
The
something
statement-
simple.
the
Let's
statement that G equals
A-
E dagger E breaks down at the exceptional point.
Sure.
Well,
That's
the thing is, it doesn't break down at that point. You can still find a metric. It's
No,
just like it breaks down only when you chose the wrong metric, actually.
but we cannot always find a metric.
In fact, we can do that.
You're
But
telling
using this
us
field
we
equation.
can map any non-Hermitian Hamiltonian to an Hermitian one?
Yes, exactly.
How is that possible? We know
no.
that non-Hermitian Hamiltonians can have complex eigenvalues. When we map them to an Hermitian one, they must have real ones. How does that work?
No. The Hamiltonian itself can have real eigenvalues, but I think I should show
You don't need,
this one.
you just have to say that you can bring it to a diagonal form, but you can't bring it to a form where all the eigenvalues are real.
Well, actually,
That's another
it's-
statement.
Exactly.
Yes, this
They're
form
not real.
works for diagonalizing.
Well, Hermitian is not diagonal. That's something different.
Yes, but it can be diagonalized.
The observables, well, after transformation, not just the observables, all the operators are transformed with this. So it turns out that if you transform a Hamiltonian, which is non-Hermitian, which has complex eigenvalues, they still have the same eigenvalues in the transformed space. But in this case, you're not transforming a non-Hermitian Hamiltonian into a Hermitian Hamiltonian. It's the evolution operator, which is this one. This one is real. This one is Hermitian.
Oh, I see. This is what people call, when your Hamiltonian is time dependent, what people call the energy operator, because it's different from the Hamiltonian.
Exactly. Yes.
Okay, that's an observation people made, that in that case you can cross actually from one regime to another.
Mm-hmm.
But if your metric or the epsilon is not time dependent, then this would not work.
But exactly that I agree with you.
Okay. Thank you.
You're welcome.
More questions, comment. George has a comment. You're mute, we can't hear you.
Okay, can you hear me now?
Yes.
Fine. Okay, let me just make a very brief introduction, because I'm working in phenomenology and on meson resonances. And if you look at mesons from the particle data tables, you see that most of them are unstable and they decay into other mesons. So if you have a meson decays into two mesons, so it can be considered a resonance in the scattering of two mesons. So if you develop a formalism for that, you can have an S matrix, which is unitary for your real energies, but then the resonance shows up as a pole on the second Riemann sheet, okay? If you continue, analytically continue the S matrix. So that's fine. I've been working on such models, multi-channel models, because usually mesons decay into more than two options of other mesons. They are called channels. So you need a multi-channel formalism. The problem starts when you have many mesons which have final states that have more than two mesons, 3 or 4. Then it becomes very difficult, because to have a scattering equation with 3 or 4 particles in the final state, they exist, but it's extremely difficult. Okay, so when then the particle data tables, they come to our rescue, because in many cases you can see that final states which have, say, 3 or 4 mesons, they can be considered final states with 2 mesons, which are resonances, intermediate state resonances. So if I could describe the scattering of 2 unstable mesons, which then produce a meson resonance in the intermediate state, that would be fine. The problem then is that, of course, if you have a resonance in a final state, it has a complex mass. So if you do that, if you have some model with complex masses in the final state, initial final states, the S matrix is not unitary anymore. So in the kind of models I've been working in, the idea was, okay, try to re-unitarize the S matrix. So it's not working at the level of the Hamiltonian, but on the level of the S matrix. It would be useful if I could share a screen. Is that possible?
So should I stop?
You can do this now.
Okay.
Can I share a screen?
You can do it now.
Okay, let me see. Can you see it?
No.
No, not yet.
No?
Now?
No.
No, it's not sharing. Okay, I don't want to waste too much time. I can then send the reference to the speaker and maybe other people are interested. Let me just try to explain it quickly. So you simply work out the model and you get an S matrix, which is not unitary, but it's still symmetric because you have time reversal invariance. So using that, you can apply Takagi decomposition or factorization. It's from the 1920s, a Japanese mathematician. So you can write an arbitrary symmetric complex matrix as the product of the transpose of a unitary matrix, a non-negative real diagonal matrix, and the unitary matrix again. And then you can express this diagonal part in terms of the product of the Hermitian conjugate of the S matrix times the S matrix. And then with a relatively simple derivation, you can redefine your S matrix, making use of this unitary transformation. And then you get an S matrix, or you get an S prime matrix, which is both unitary and symmetric. Now, this is, of course, an empirical redefinition. And in the paper that I would like to show you, but I cannot share it, this has been applied to a typical case of a very enigmatic meson resonance, namely the X3872. I mean, it won't tell you anything. It is one of these famous mesons that have been found, which has very typical properties. It looks like a tetraquark or whatever it is, doesn't matter. The problem is that this meson resonance, it has a decay mode, a very important decay mode, which involves another resonance. So this is a typical case that you could apply such a redefined S matrix. And we have done that in that paper. I have done this with a long-time collaborator from Coimbra, from Bever, and with a PhD student, Susanne Koit. And it worked remarkably well, at least in that case. So, and I see some vague similarities with your procedure, although you work on the level Hamiltonian, I work on the level of the S matrix. So, I mean, if you're interested, I can send you.
Yes, that would be great.
Yeah, okay, fine.
May I make a comment on this?
Yes.
Yes, please.
To say that the S matrix is unitary,
yes,
is to say that the in and out states are complete. Not that SS dagger is one, but that you have a complete set of states.
Yes.
Now, if you introduce resonances, then you have to ask, well, should I include them in the complete basis? And the answer is, well, you can only do so if you're looking at scattering for times shorter than the decay time. And that's okay. can do
Yes, exactly. So in fact,
what
that's
you've
what.
got to do is if they decay into another state, which then decays again, you've got to define at each time what is the complete basis.
Right. So in fact, that's precisely what and in a sense, the experimentalists have been doing. They have verified that certain final states are, so for longer times, that end up for the long times in terms of 3 or 4 mesons. If you look at shorter time scales, they look like 2 resonances, or 1 resonance plus a stable particle.
Yes. Now,
this is really far off now from Vielbein.
Yeah, sorry. Okay.
We are cutting off the speaker, I think.
Okay. No, I'm not cutting off anybody.
We should give the speaker back the stage. And if you have concrete questions to the talk, I think this should be still invited.
Could you please send this referee or this reference to Andreas, for instance, and Andreas can spread it among the community, because this reference might be interesting. Just look at it to see the technical details.
Super spreader.
I will do.
Would be very nice. Thank you very much.
Any more comments, questions, but related to the talk?
Yeah, but I think the question that was just asked about the scattering does relate to the talk, but it relates to the PT realization where there are complex energy.
Chia-Yi, you want to answer this question related to your talk?
Yeah, I didn't get the question actually.
Okay, well, let me try to paraphrase it. The question basically is, how do you handle unstable states? Now, in the PT theory, we know how to do that, because you can define everything that Chia-Yi, that you've done with a G that's not positive definite. That's the question I was stating before. And then unitarity is not SS dagger equals 1, but it's SG S dagger G dagger equals 1. And that's what we call pseudo unitarity. So there is a prescription within the formalism that Chia-Yi has been describing to describe unitarity in the presence of unstable states.
What
but
about
states that decay, unstable states. But it involves this operator G, where it doesn't bring you to a Hermitian Hamiltonian. It can bring you to a Hamiltonian where the eigenvalues are in complex pairs. And what I was asking was, presumably, but not obviously, that case corresponds to G not being positive definite. And I think that's a correct way of handling decays. It's not the way that, what is it? George has been describing what's commonly done in the high energy community, and it's certainly not that way. But I believe that George's question is how do we connect that way that the standard phenomenologists use to Chia-Yi's presentation? And the answer is this operator G has that information buried in it.
Yeah,
I think that's the answer.
Actually, I don't have the answer to that question there, because now we're breaking this the positivity, and the G being positive definite, and this is a little bit different from what we expected.
Well, I'm just guessing that that's what you do. I don't know for sure.
Yeah, for now, if there is something decaying, then I don't really know how to deal with that.
Very few systems in nature that don't decay.
Yeah, I understand.
In fact, we're not even sure about protons anymore.
So I guess I don't have any comments on that.
Okay.
So.
Any more comments, questions?
Can I just a couple of very, very brief. I mean, the question of whether or not you can interpret a PT symmetric Hamiltonian in the unbroken regime as being equivalent in some sense to a Hermitian Hamiltonian. Okay, that's a very complicated question. I mean, maybe what you're doing here is providing a way to understand that, but the way we first thought about it is that there is a similarity transformation that converts it to a Hermitian Hamiltonian, okay? But that similarity transformation is unbounded. And that's the key question, okay? So for a 2x2 matrix, there isn't any problem. But for a continuous system, there is a serious problem because it's unbounded. And when you have an unbounded operator, mapping a Hilbert space of vectors is a very complicated procedure, and there may be effects associated with that unboundedness of the transformation. Okay, it's not obvious that you can say that a PT symmetric Hamiltonian is truly equivalent to a Hermitian Hamiltonian. The second comment is that going from an unbroken region to a broken region is also a very complicated transition because it isn't analytic. Okay, when you cross the boundary between a PT symmetric Hamiltonian and a PT a PT unbroken Hamiltonian and a broken Hamiltonian, that is not an analytic continuation. Okay, that is definitely not an analytic continuation, and therefore many assumptions about things being preserved when you go, say, from an unbroken regime to a broken regime, they are not, okay? And there are discrete changes that occur. Now, maybe you can think about that as a natural boundary or something like that. But, you know, it looks like all you're doing is just changing the value of a continuous parameter. But you're not. You're simply taking a different value of that parameter. And that's a very complicated issue. I mean, those are two very different theories, what is going on in the unbroken regime and in the broken regime, okay? And getting from unbroken to broken is not just a simple change of parameter, okay? And so, I mean, there's a lot of stuff to think here. Maybe you've provided a continuous route to go from unbroken to broken. Maybe that's the point of what you're doing. You're finding some sort of continuous path, but I have to think about this very hard.
I think he is not doing a similarity transformation.
No, that's what I'm saying.
He's not doing a similarity transformation. He's doing what we do in the time-dependent case, because there is the gauge-like term, this connection term. And we have many examples in the time-dependent case where we know we can actually go from one regime to the other.
Right.
Yeah.
Right.
Yeah.
So
we know many examples.
Right. So maybe that's the value of what we are talking about, how to actually really go, how to relate a broken and an unbroken regime. That may be.
Well, we know how to do it with a time-dependent metric, and that's precisely what he's doing.
And if I may weigh in, may I share
sure.
my screen, right? Again.
Yeah, you can.
Okay, so I think it's this one. So I hope that you can see my slides here. So within this, so I mentioned this thing here. So we have this this evolution in Q direction, and that this Q can be the parameter that take us from a PT preserved PT symmetric region to PT broken region. And what we found is that this K is actually singular. Well, in some coordinates, it's singular when it hits the exceptional point.
Exactly.
So the thing is, it looks a lot like the horizon in this black hole analogy.
Yes, exactly. It's one-to-one.
Yeah. So
it's one-to-one because your similarity transformation that you are using the inverse, and this inverse is not defined at this point. You should rewrite it in a different way so that you can just use also situations or handle situations when the metric is changing in such a way that you can have zero terms on the diagonal.
If I can make a comment on Carl's first comment. When I discussed this earlier on in the talk, I did qualify it by saying that, well, the transform to Hermitian requires the similarity transform to exist. So the question that you can ask is, could there be a PT system with that you can't get to Hermitian by a similarity transformation.
It is not the similarity transformation.
No, wait.
Not what he's doing.
No, I know that.
But you still use the word.
Yes, fine. I know that in the conventional language, there is an issue of whether or not the similarity transformation exists or not. So now Carl is asking, is there a case where you have different geometric considerations so that you can't, in the geometric case, get to Hermitian? And one of the things I had suggested was maybe in that case, you have a Riemann non-zero tensor, a non-zero Riemann tensor, because it can't be brought to Cartesian. And so maybe that's the geometric analog of the non-existence of the similarity transformation. That was the point I think Carl was asking, and that's the point that I was commenting.
That's right. That's well said. I mean, that's a very interesting question.
Yeah, but you can rewrite all this similarity transformation in a very simple way. You should avoid the inverse of this matrix. You can, for instance, you can write down a kind of similarity transformation. It looks like a similarity transformation, but it's not a similarity transformation. Just take on one side a Jordan block and on the other side a diagonal element. And you get matrices which are not invertible, where you can find a relation, not a similarity transformation, but a relation between them. And this holds. Everything
but this is
fine.
Not the similarity transformation.
Exactly.
Chia-Yi, could you show us your slides again?
Exactly.
Yeah, sure.
It's not the similarity transformation.
No. It's not a similarity transformation. It's a relation between them.
Yeah. If you go back, Chia-Yi, this one, the one below, yeah. So the epsilon, if it's not time dependent, then it would be the analog of a similarity transformation. Then the epsilon is just what people call the Dyson map. But epsilon is t dependent, so it's the analog to the time dependent Dyson equation. And in that case, we don't have a similarity transformation anymore. The operator on the left is not a Hamiltonian, it's the energy operator.
Exactly, yes.
Yeah, it's a different, it's not a similarity transformation. Okay, maybe we should leave it here. Yeah. Any last comments? Any last remarks? Okay, Chia-Yi, thank you very much.
Thank you very much.
Your talk triggered a lot of discussion, so thank you.
Thank you.
Thank you.
Please send us your slides. Yeah, we make them available alongside your talk. Yeah.
Okay, thank you very much.